This is Neil Patwari. In this video segment, I'm going to derive a general formula for the probability of symbol error in M-ary PAM. And over the next several lecture videos, we're going to take what we've learned about the conditional distribution of the received vector x to calculate general formulas for the probability of symbol error and the probability of bit error for a variety of M-ary modulations. And we'll start with this M-ary PAM video, which is a one-dimensional modulation, and then we'll move on to two-dimensional modulation, which will cover a lot of QAM and PSK modulations. Finally, we'll move on to M-ary FSK, which has more than two dimensions. So in 8 PAM, we'll have a signal space diagram like this. And while this is for m equals 8 PAM, you can imagine what this would be for general M-ary PAM, where I have 2A separating each set of neighboring symbols. And the 8 symbol values here are from minus 7a to plus 7a. They're centered at 0. What we're going to assume is that noise is Gaussian with 0 mean and variance n naught over 2. And we're going to assume that the m different symbols are equally likely. Using the law of total probability, we're going to write that the probability of symbol error is a sum of the product of the probability of symbol error given hi times the probability of hi. And this is because the hypotheses h0 through h sub n minus 1 forms a partition. That is, they don't overlap, and exactly one of those events always happens. And these symbols are equally likely, so the probability of hi for every I is the same as every other hi, so it's going to be 1 over capital M because they're exactly equal. Now 1 over m, I'm going to bring it out. The thresholds here, because we have equally likely symbols, the thresholds are going to be halfway in between each neighboring pair of symbol values. So if the symbol values are minus 7a and minus 5a, then the threshold is going to be at minus 6a. So first let's consider when symbol 0 is sent. Our probability of symbol error given h0 is what happens when I send minus 7a and I receive that minus 7a plus noise, plus the Gaussian noise. And to make an error, when I send minus 7a, I have to exceed this threshold minus 6a, because if it was less than minus 6a when I receive it, I'm going to decide symbol 0 was sent. So this is the probability that my x value that I measure, the 7a plus the Gaussian noise, is greater than minus 6a. And I know that it's not a standard normal random variable, that is, x is not a standard normal random variable, and I only have formulas for the probability of x being greater than something if it is a standard normal random variable. So I do this trick where I subtract the mean and I divide by the standard deviation. This side is a standard normal random variable. I'll call, as I do typically, call my standard normal random variable z. It's this fraction a divided by square root of n naught over 2. And once I have this probability of a standard normal random variable being greater than a threshold, this greater than part is the critical thing here. This means that I need the q function. If it was a less than, I'd need the phi function. And that's just when symbol 0 is sent. When symbol 1 is sent, I have two ways I can make an error. I'm going to have this value centered at minus 5a, but if it goes below minus 6a, I'm going to mistakenly record that symbol 0 was sent. And if it goes above minus 4a, then I'm going to pick one of these symbols here that is also an error. Okay, so I need to think about the probability that x is less than minus 6a and the probability that x is greater than minus 4a, given that symbol 1 is sent. I can convert these probabilities into the probabilities about standard normal random variables, just like I did before. The mean is minus 5a, so I'm going to, when I subtract the mean, it's going to be minus 5a. I skipped the step of doing this to both sides of x, and I just replace that x with z, which I know it's going to come out to be. That is my variable name for a standard normal random variable. And here, I have z being less than a certain value. This becomes a minus a on top because I've got a minus 6a plus 5a. But what this becomes then is a phi function of minus a divided by square root of n naught over 2. And the other side becomes this q function of plus a. This one is a minus 4a plus 5a, so it becomes another just positive a. This phi function is the same as the q function for a positive a divided by square root of n naught over 2. Okay, just negating the argument gives me the same thing because we're talking about these tails of a standard normal random variable, right? So this is, if this is a standard normal random variable and this is a minus z value, and I'm trying to find the probability that's less than this, well, it's symmetric, so it's the same as the probability that it's greater than the positive same threshold. So this becomes the q function of a over square root of n naught over 2. I've got another one over here, so this becomes 2 times that. And in symbol 1, we're going to end up with the same thing if I had said symbol 2 was sent. It's got the same thresholds. They're both exactly 1a away from that circle. Same as if symbol 3 was sent, and so on, all the way up to symbol S6. And then S7 is exactly the same as symbol 0 by symmetry. It's got a threshold that is 1a away from its mean. And so it's going to also end up with this first probability of error, the single q function. So I have these two different expressions. This one applies for symbols 1 through S6, and this one applies for symbol 0 or symbol 7. So when I go back to this expression, our original expression for the probability of symbol error, I'm just going to have to account for these two different formulas, and I'm going to divide by 8 in this case. So for my m equals 8 case again, I'm going to say that the probability of symbol error, I'm going to have these two cases of having this function. And in addition, I'm going to have 1, 2, 3, 4, 5, 6 of these cases where my error is 2 times the same q function. 2 of these, 6 of these. And when I add them together, I just get 14 of those q functions, and I divide them by 8, and I have my expression. But let's talk about m in general, because my symbols, if I had higher values of capital M, I would have more symbols, but I would always have symbols separated by 2a. The threshold would always be halfway in between them, that is a away from the symbol value. And I would always have the symbols at the end having this probability of error, given that the symbol on the end was sent, and I'd always have the symbols in the middle, all capital M minus 2 of them, having this probability of error expression. Okay, and that's going to simplify, which is going to make it m minus 1 times 2. There we have it. We have a general expression for the probability of symbol error in M-ary PAM. But a is just a constant that we've picked. When we compare this to other modulations that don't have the same geometry, we want to be able to talk about what the probability is compared to that. And it's going to be hard to compare that when a is just some arbitrary number that we've decided is how far apart we separate symbols in M-ary PAM. We want to talk about, instead, we want to talk about the probability of error as a function of the energy per bit rather than the a value here. So what we're going to do is we're going to write an expression for the energy per bit. And as we said before, it's 1 divided by the log base 2 of m times the energy per symbol. And in a previous video, we showed how the energy per symbol is given by m squared minus 1 times a squared divided by 3. So when I find a formula for a squared, it's going to be flipping these around, and I'm going to have 3 times the log base 2 of m divided by m squared minus 1 times the energy per bit. And this is going to help me because this probability of symbol error, I can write this q function by taking the square root to encompass the entire fraction by squaring the a and putting the 2 up top instead of in the bottom of the numerator. So I've got 2a squared divided by n naught. I haven't changed anything there. Now I'm going to plug in this expression for a squared. And I have an expression where I have the 3 times the 2, or 6 times log base 2 of m divided by m squared minus 1. And I have the EB on top and the n naught in the numerator. This expression, EB over n naught, is going to repeat itself in every probability of symbol error and every probability of bit error expression that we have. And they're both energies. They're both measured in joules. And so this becomes unitless, and it becomes a representation of how much energy we have in the actual signal that we want to hear versus how much energy is in the additive thermal noise that contributes to our receiver. And that fraction then is going to determine the probability of error given any particular value of m. So let's draw what this function turns out to be. Here you can see the expression. We've got 4 different lines here, one for each different value of m that I was plotting, m equals 2 through m equals 16. On the x-axis, we're listing the energy per bit divided by n naught. This EB over n naught ratio is given in dB, decibels. Okay, so it's the 10 log 10 of the linear value of EB over n naught. And on the y-axis, we've got another log scale for the probability of symbol error. We've got anywhere from every bit in error to 10 to the minus 6th, 1 in a million symbols is received in error. And then we've got a line showing us this expression for the probability of symbol error for each value of m. You can see that as m goes higher, from the green line to the black line to the blue line to the red line, we need more energy per bit to get the same probability of symbol error. And on the other side of that equation, if I have a given value of energy per bit, this is how much energy per bit I could receive at my receiver, and I can get no more. Well, then I can decide on my value of m. As I go higher in m, I get more bits per symbol, and thus I'm able to send a higher data rate. But as I do that, my probability of symbol error goes up. And this will be the trade-off that we will be talking about for a while, probably the remainder of this course, that when we design a communication link, we have to take the energy per bit into account. We have to take a desired probability of symbol error into account, and we have to trade that off with the data rate and the bandwidth efficiency that we want to have. And we'll provide more expressions for the probability of symbol error and other modulations besides PAM.